Hello friends, in this video we are going to discuss about standing waves, and we are going to obtain the conditions for obtaining nodes and antinodes on a string vibrating transversely fixed at the both ends. Okay, so this is our topic to be discussed in this video. So before we start, please do subscribe the channel, hit the thumbs up button, also share it to friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. Now you see two waves of same kind, okay, are traveling in opposite direction but along the same straight line. Okay, this is in this direction, this is in this direction, and along the same straight line but in opposite direction, having same frequency, same wavelength, right, and same amplitude. Then due to the superposition of these two waves, a new set of waves will be formed, and those are called stationary waves or standing waves, right? So here in this case, the resultant waves do not that produced in this manner, due to the superposition of two waves of same kind but traveling in opposite direction, that kind of resultant wave, which is known as a stationary wave, do not propagate in any direction, nor there is any transfer of energy in the medium. Okay, in the stationary waves there are certain points of medium, okay, where permanently rest. That means displacement is zero all throughout. That means, let me show you something. Now you see these are particles in a medium. When a wave travels, okay, that what happens, these particles oscillate like this, okay, for this kind of wave, right? But when standing wave is formed, there will be certain position where the particles at that position will not oscillate. Okay, so hope you have understood this. So now let me write the definition. Here is the definition, and as I have already told you that in standing waves are also known as stationary wave. Okay, there are some certain points where in the medium where there will be no displacement. Okay, those points at those points the particle of the medium do not displace, okay, and which are permanently at rest. Okay, these points are called nodes. Okay, similarly there are some other points which vibrate about their mean position with largest amplitude. Okay, these points are called antinodes. When two waves travel in opposite direction of same kind and with the same velocity, okay, along the same straight line, there will be after superposition there will be some points which will vibrate with maximum amplitude, and there will be some points which are permanently where particle of the medium will be permanently at rest. Those are called nodes, and these points which will vibrate with largest amplitude, that will be known as that will be called antinode. Okay, so hope you have understood this. So now let's discuss the next part of this topic. So that is what nodes and antinodes, the position of conditions for nodes and antinodes on a string vibrating transversely fixed at both ends. Suppose there is a string which is fixed, its two ends are fixed, right, and it is vibrating. We need to find the conditions for nodes and antinodes here. Okay, let's discuss about this. So here you see, suppose this is a string which is fixed at both ends, and its length is L, and it is said to vibrate. Okay, so now let us consider let me draw this figure here. Let me consider this direction is positive x-axis, positive x direction, let me consider that way. Now let the wave pulse moving on the string from left to right. A wave pulse is moving from left to right, okay, on the string. From left to right means from along positive x direction, along positive, let me write this one, along positive x direction, along positive x direction, right? And let it be represented by this equation y1 x comma t is equal to r sine omega t minus kx, right? So here you know that r is amplitude here, and omega is angular frequency, and t is time, we know x is the position at time t, right? And y is the displacement here, and the k is the, you know, this is propagation constant, right? Y is the, here y1 is the displacement of the particle at position x at time t, right? Okay, hope you have understood this. Okay, now here you see, let me, now what happens, this pulse is sent from left to right, then it strikes this fixed end and it will be reflected back, right? It will be reflected back, right? And when it will be reflected back from this fixed end, then there will be a phase change that will which is equal to pi, okay? When there is closed end, when there is fixed end, and if the wave reflected from that end, there will be a change in phase that will be equal to pi, right? So here we're going to write that as there is a phase change of pi, so that's why pi radian, let me write here radian, pi radian. So on reflection at the fixed end, on reflection of the string, so the reflected pulse, so the reflected pulse will be represented by, that is traveling from right to left. This is the initial pulse that's reflected back from right to left, right? Okay, reflected wave pulse traveling from right to left, that means along negative x direction, right? Along negative x direction is represented by, let me write here, is represented by that will be represented by y2 xt is equal to, amplitude will be same, okay, sine, so you see omega t, now the direction is changed, so that's why this minus will be plus, right? This minus will be plus in this case, plus kx, as there is a phase change, so that's why we have to write plus pi. Phase change is pi, plus pi phase is, phase is changed by pi radian, so that's why if we apply the ASTC rule, so pi plus this, that's going to be minus cos, sine because this is pi even multiple of 90, so we're gonna get minus r sine pi, sorry, not pi is not required now, omega t plus kx. That's what we're gonna have, right? Now according to the superposition principle, right? According to the superposition principle, so I made the 2 here. According to superposition principle, the resultant y, okay, the resultant y, or you can say the resultant displacement, at time t and position x is given by the resultant displacement is suppose y, so that y will be given by y1 plus y2, right? Y1 plus y2. That means you can you can write like this way, function of x and t. So similarly these two as well, right? So now let's add this one and this one. So here y x comma t, y1 is equal to r sine omega t minus kx, right? This is y1, right? This is y1. And now let us put y2 is minus of this one, right? So the plus sign will be minus r sine omega t plus kx, in this case plus kx. Now let us use this identity. The identity is sine c minus sine d. Sine c minus sine d is given by is equal to 2 cos c plus d by 2 into sine c minus d by 2. Let's apply this here, sine c sine d. Okay, r is to r, if you take the r common, then this will be of this form, so r is taken as common, right? Hope you have understood this. So now apply this identity. Okay, so if you apply that identity y x comma t, then r, so that's going to be equal to within bracket sine c plus d, this one plus this one, plus kx minus kx will be cancelled on adding these two, then we will get 2 omega t, and because of this formula from here we're gonna get 2 will be cancelled. So here what we're gonna have this sine omega t, right? Then that should not be sine, cos. Let me show you, cos c plus d, that is omega t minus kx plus d is omega t plus kx, right? Divided by 2. Here plus kx minus kx gone, omega t plus omega t, 2 omega t, 2 cancel, so we're gonna get cos omega t only, right? So it's gonna be cos omega t, then into sine c minus d. If you subtract this 2, that means omega t minus kx minus omega t plus kx divided by 2, then you see on removing this bracket, this plus sign will be minus, right? This plus sign will be minus, so omega t plus omega t minus omega t gone, minus kx minus 2kx, so 2 to cancel, we're gonna get sine minus kx. Okay, sine of minus kx, we know minus sine of minus theta is minus sine theta, so that's why at the end we're gonna get minus r cos omega t and sine kx. That's what we're gonna have, right? Hope you have understood this. So let me rearrange this, let me copy this and let me go to new slide. So here is the last result we have got. If we rearrange this y of x comma t, let me write minus r sine kx cos omega t. So here you see, just let me write it properly, cos omega t. So here this one is amplitude of the resultant wave. Sorry, I missed something. Okay, there was 2 in this formula, so I have missed that 2. There should be a 2, I think. Okay, 2. So here you see, this 2r sine kx is the resultant amplitude. Okay, and this equation is the resultant displacement, right? This gives the resultant displacement. Okay, now this string, the 2 ends are fixed, the string of these 2 ends are fixed. Then if it vibrates, the first mode of vibration is this, something like this. Let me show you this. Here you see, as these 2 positions are fixed, so these 2 points are permanently at rest. So these are the position of nodes, right? So that's why you see, if we take this is x-axis and this is origin and this is x, then if this length is suppose L, if this length is L, then this position will be x is equal to L, right? This one will be x is equal to L. This position is x is equal to L, right? So now you see here, at x is equal to 0, at x is equal to 0, so that means the fixed end on the left side, or you can say at the fixed left end, right? So here if you put x is equal to 0 here, that will be sine 0, sine 0 is 0. So in that case we're gonna get y is equal to 0, the resultant displacement will be equal to 0, right? On the other end of the string, so here you see, as y is equal to 0, this is position of node. Okay, this end is node, right? At x is equal to L, that means the right end, the right fixed right end. Okay, here what we're gonna get, y is equal to minus 2r sine kx, instead of x there will be L, and cos omega t, right? That's what we're gonna get. Now you see, since it is fixed, so it must be a position of node, must be a position of node, because it cannot displace, right? So that's why this part, that this displacement must be equal to 0, and it will be possible when this amplitude become equal to 0. That means sine KL must be equal to 0, right? Sine KL must be equal to 0, and sine KL will be equal to 0 when this KL will be equal to n pi, because the general solution of sine theta is equal to 0 or sine x is equal to 0 is x is equal to n pi, right? Hope you have got in mathematics, because sine n pi, where n is equal to 0 1 2 3 so on. Okay, so sine 0 0, sine 180 0, sine 180 means sine pi 0, then sine twice pi is also 0. Okay, sine twice pi is also equal to 0, then sine 3 pi is also equal to 0. So remember, sine n pi is always equal to 0. So now if that is the case, from here what we're gonna get, we're gonna get KL is equal to, therefore KL is equal to n pi. Now let me copy this and let me go to a new slide. Now you see, we know that propagating constant K is equal to 2 pi by lambda. Let me use this result here. So then what we're gonna get, we are going to have 2 pi by lambda. Lambda is wavelength, n pi. Lambda is nothing but wavelength, right? So now, sorry, I missed the L, I think. Yeah. So from here what we're gonna have, we're gonna get lambda is equal to 2L by n. That is what we're gonna have, where n is equal to 1 2 3 dot 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 so on. Okay, this corresponds to first comma second comma third normal modes of vibration, right? Let me write this way: normal modes of vibration. Okay, of the string. So here n cannot be taken as 0, because if you take it 0, and this is going to be not defined. So that's the reason here. So now here you see, first normal mode of vibration. First normal mode of vibration. First normal mode of vibration. Now you see, suppose lambda 1 is the wavelength of the standing wave set up on the string correspond to n is equal to 1. Now you see, if the same string, if it vibrate like this way and if it vibrate like this way, right, in both the cases wavelength is different, right? Because here you see, here we can see only half of the wave, okay, and here we can see the complete wave within the same length L, right? So here the L is equal to lambda by 2 and here L is equal to lambda. So this lambda in this case and lambda in this case, two different length here. Here we have taken lambda 2, let me take this as lambda 1, okay? That first mode is taken as lambda 1. So hope you have understood this. Okay, lambda 1 is the wavelength corresponds to n is equal to 1. So if that is the case, then we're gonna get lambda is equal to 2L, because you see, in case of first mode, this is the first mode of vibration, right? First normal mode of vibration, this length is L, right? If L is equal to lambda by 2, then lambda will be equal to 2L, right? Correct. And similarly L is equal to, we can write lambda by 2, right? So now you see, frequency of vibration. So let me write this one lambda 1, okay? Instead of lambda, let me write lambda 1. And frequency of vibration let me write simply frequency nu 1. We know that speed of wave v is equal to nu lambda, so that's why nu will be equal to v by lambda. So here we're gonna get v by lambda 1. Okay, now where v is the speed of the wave, okay, so lambda is equal to 2l, so we can write that nu 1 is equal to v by, so let me write this way, nu 1 is equal to v by 2l. That's what we can write. Hope you have understood this. Okay, and this is l is equal to 2 lambda, right? So now let us discuss about second mode of vibration. So same string of same length, right? Now in second normal mode it will vibrate like this. So here we're gonna get 3 nodes, this one and this one, 1 to 3 nodes. So here length is same l, same string, but in this case l is equal to lambda. So here we're gonna take lambda 2. Okay, already we have taken first one, lambda 1. So this is second normal mode. Okay, number 2, second normal mode of vibration. So first normal mode of vibration is this, right? This is also known as fundamental mode of vibration. This is also known as fundamental mode of vibration, right? This is also called fundamental mode, right? Now here second normal mode of vibration. Second normal mode, okay, of vibration. Okay, so we used to call it first overtone or second harmonic. This is also known as first overtone in or you can say second harmonic, or you can say second harmonic. Okay, so this should supposed to be a second harmonic, right? Now you see, in this case, let lambda be the wavelength, wavelength corresponds to n is equal to 2, right? N is equal to 2. Then from this equation, so let me write this as equation number 1, right? Have I given any equation number? No, so let it be 1. Okay, so here from 1, okay, equation number 1, we have got this. And if n is equal to 2, then equation number 1, what we're gonna get, lambda 2 from equation number 1. If we apply the equation number 1, then lambda 2 is equal to 2l by, okay, that's supposed to be, yes, 2l by 2, because we have got lambda is equal to 2l by n, right? So now n is equal to 2, so that lambda 2 will be 2l by 2, which is gonna give you l, right? So here lambda 2 is equal to l, and frequency nu 2, that's gonna be equal to again v by lambda 2. Lambda 2 is l here, so v will be equal to nu 2 is equal to v by l. That's what we're gonna have. Okay, So this also can be written as this way: 2 into v by twice L, and v by twice L is equal to nu 1, right? This is v by twice L is equal to nu 1, so that's why it can be written as 2 nu 1. That means v2 is equal to 2 times of nu 1. You can write that one also. So hope you have understood this. Okay, right? So now let's discuss about third overton. So same string, same length, but the pattern will be like this. So this is one complete wave, then half of the wave. Okay, now this will be vibrating like this way. Okay, so same length of the string L, right? Now here in this case L is equal to 1.5 of lambda. So let me take lambda 3 in this case, corresponding to n is equal to 3. Okay, so this is third normal mode of vibration. Okay, third normal mode of vibration. So here if we consider, let lambda 3 take lambda 3 is equal to the wavelength corresponding to n is equal to 3, right? In that case, from equation number 1, what we're gonna write lambda 3 is equal to 2L by 3. 2L by 3, that's what we're gonna have, 2L by 3. In that case, frequency nu 3 is equal to, so last one what we have written, okay, nu 2. So nu 3 is equal to v by lambda 3, that's gonna be equal to 3v by 2L. That's what we're gonna have on by using this value, right? Hope you have understood this. So this can be written this way: 3 times of v twice L, and v by twice L is nothing but nu 1, so it's gonna be 3 nu 1. Okay, so this is known as third harmonic. Third normal mode is also known as third harmonic, or second overton, right? So hope you have understood this. So frequency of n-1th overton. So for second overton, here we have got 3. So for third overton, here we're gonna get 4, right? So therefore frequency of n-1th overton will be nu n is equal to, now here we're gonna get n times of nu 1, as here we are getting nu 3 is equal to 3 times of nu 1. Similarly here we're gonna get nu n will be equal to n times of nu 1, and lambda n wavelength will be equal to 2L by n from equation number 1. That's what we're gonna have. Now let's find the position of nodes and antinodes. Okay, let me take a new slide. Okay, just give me a second. Right, in order to determine that, let me draw all the 3 modes. So here is the first mode, this is the second one, and this is the third mode. Here you see, let me show you the position of nodes. Right? So now you see, for the first mode, position of nodes are x is equal to 0 and x is equal to L. Here we are getting 2 nodes, this one and this one. Okay, for the first mode, x is equal to 0 and x is equal to L. These two are the positions. And for the second mode, so x is equal to 0, here we have got a node, and x is equal to L, here we are getting a node, and also we are getting a node at x is equal to L by 2, right? This total length is L, right? So here half of L, right? Hope you have understood this. So for the second mode, x is equal to 0, L by 2 and L. Similarly for third mode, what we're gonna get, x is equal to 0, this is x is equal to L. Between these two we are getting 2 more points. So here you see there are 3 equal parts. So here we're gonna get L by 3, and here we're gonna get 2L by 3, right? So x will be equal to 0, then comma L by 3 and 2L by 3, and this L is nothing but 4L by 3, so 3L by 3, so 3 cancels, so L, right? Hope you have understood this. So we have got L. So similarly, if you find the fourth mode, then x will be equal to 0, then L by 4, then you're gonna get 2L by 4, 2L by 4 means L by 2, then you're gonna get 3L by 4, then you're gonna get 4L by 4 means L, right? And so on. Similarly, for fifth mode, you're gonna get x is equal to 0, L by 5, then 2L by 5, then 3L by 5, then 4L by 5, then 6L by, 5L by 5, that means L, right? So similarly for n mode, you will get 0, here L by n, then you're gonna get 2L by n, then you're gonna get 3L by n, then at the end you're gonna get NL by n, that means L, right? So that's what we're gonna get. So we can say that in general form, what we can write, the position of nodes, we can write this way. Therefore the position of nodes for nth mode is given by x is equal to 0, L by n, 2L by n, 3L by n, dot at the end L, right? So now let's find the position of antinodes. Okay, so now let me copy these diagrams and let me take a new slide again. So here you see the position of antinodes. So this is the position of antinodes, right? Here this is x is equal to L by 2. So this is position of an antinode, this is also position of antinode. So now you see how to find the position of antinodes here. If you see here, this L is divided now into how many equal parts? 1, 2, 3, 4, right? So 4 equal parts. So that's why this position is L by 4 and this position is 2L by 4. So that's why we are getting L by 2, right? 2L by 4, and this one 3L by 4, right? So these are the positions of antinodes for second mode. For the first mode, this is the position of antinode, and for the third mode, here you can see now how many parts are there. You can see this is first, second, third, fourth, fifth, sixth. 6 parts are there. So what you can write, this position is your L by 6. This L by 3 means 2L by 6, right? And next 3L by 6, that means which is L by 2. 3L by 6 means you can say L by 2, L by 2. And 2L by 6 means this is L by 3, this is L by 3, right? So at L by 3 we are getting nodes, not antinode. At L by 2 we have got antinodes. Then again these are the position of antinodes. Again this is L by 6, then 2L by 6, this is 3L by 6, which becomes L by 2. Then here this one will be 5L by, sorry not 5, 4L by 6, this one 4L by 6. On cancelling it becomes 2L by 3. Then after 4L by 6 we're gonna get 5L by 6. Okay, these are the positions. So here you see, for the first mode, position of antinodes, position of antinodes, position of antinodes for the first mode. What we're gonna get, x is equal to L by 2. And for the second mode, of vibration, here we're gonna get x is equal to L by 4 and 3L by 4. And in the third mode, here in the third mode, right, for the third mode, what we're gonna get, x is equal to L by 6, then L by 2, which also can be written as 3L by 6, and next one 5L by 6. So that's what we have got. So what will be the position of nodes, antinodes? What are the position of antinodes for nth vibration? Okay, for nth mode of vibration. So now you see, for the first mode you have got 2 here. For the second mode you have got 4 here, that is 2 into 2. For the third mode you have got 6, that means 2 into 3. So what you can write for the nth mode, you can write x is equal to L by twice n, comma, then you can write 3L by twice n, then you can write 5L by twice n, dot dot dot. You can write here it is 5, this is 6, so this is 2 into 3 times minus 1, right? So this is third mode, this was third mode, and here this is 3, so 2 into 2, second mode, 2 into 2 minus 1. So for nth mode this one will be 2 into n minus 1, right? 2 into n minus 1 L by twice n, that's what we will get. So these are the positions of antinodes. So hope you have understood this. So thank you for watching. See you in the next video. Bye bye.